We had talked about single bonds being able to rotate around the bond. The electrons are shared directly in between the two atoms that are single bonded, and so that single bond can rotate. Then we talked about cis-trans isomers. When you have a double bond is not able to rotate. So that gives rise to these things we call geometric isomers. I want to also mention this. Now, I didn't put all the hydrogens on. This is what would be the parent. The black ones are carbons. The parent is what?
Cyclohexane.
There's 6 in the ring, so it's cyclohexane. Yep. And if the, I put the hydrogens on just these two that have green one, we're going to say the green atoms are chlorines. So it looks like this compound would be 1,2-dichlorocyclohexane. Assuming that there's hydrogens on all these other carbons. Okay? If I have this compound, what's the name of this compound? 1,2-dichlorocyclohexane. Is this the same as this? This bond can't rotate, can it? These are pretty well fixed where they are. The carbons are sharing electrons between all these in a ring. And I cannot rotate. I mean, there's a little bit of ability to rotate like this. Remember we talked about the chair arrangement versus the boat arrangement for cyclohexane. And I'm breaking bonds as I try to mess with it at all. And that's physically what happens is if you put any strain on the bonds, usually the bonds will break. But anyway, we have cis-trans isomers for when there's a double bond. You also need to specify cis-trans if you have 2 or more functional groups on a ring structure. This one would be not just 1,2-dichloro, it would be cis 1,2-dichlorocyclohexane. And this one would be trans. See how the chlorine is down below the plane there and it goes up above the plane in the next one? There's a lot to remember in organic chemistry. Cis, trans. When we have to draw this as a representation, I'll try to draw the hexagon kind of flattened or squashed down. And if I do want to represent cis 1,2-dichloro, I would do it like that. That would be the cis arrangement. What would trans look like then? 1 above, 1 inside, like that. Cis-trans. And they are different. Yes. Oh, yes.
It's not showing on
And what?
It's not giving the whiteboard.
so Katie probably won't know what it looks like.
There you go, Katie.
You're welcome, Katie.
That was Jane.
Shut up.
Okay. Let's see what we get today. Probably something good. I'd like to spend almost the entire hour talking about reactions in organic chemistry. And we'll start there. Okay. This was in the reading assignment. I'd just like to go over it again with you so that if you have any questions, you can ask. And if I can just kind of explain through this maybe a little bit more than what the book did. This one was on the reading, your version of the reading quiz, I think. When you have a halogen that's added on or replaces a hydrogen in a saturated organic compound, that's called a substitution rate. That's different from halogenation. A halogenation reaction, you start with an unsaturated, the second bond breaks and you get both atoms of the halogen added on. You only get one of them in a substitution reaction. I will tell you, there are, 5 or 6, 7 maybe, reactions that we're going to talk about today, assuming I have enough time to get through them all. I strongly suggest that you get into the problems in the book and try to work through and complete the reactions that are given to you to complete in the exercises. There's a lot of information. Over the next few days, man, I'm just going to be filling your bucket. We got 3 more lecture days, Wednesday, Thursday, Friday. We have a lab on Monday, and then a quiz on Tuesday, test on Wednesday. So this is going to be a busy next week for us. And hopefully outside of class too. Okay, so you see this, this symbol right here. This looks like HV. It's not a V though. Does anybody know what that character is?
Ultraviolet.
Well, yeah, the book told us ultraviolet. I don't know why though, if they wanted ultraviolet, why didn't they just put UV? UV, right? Instead of the H. Well, it turns out that, and I know that in chemistry, I think we've taken this out of Chem 1, and I don't know that it's ever coming back. We used to talk about light. And this is a very well-known equation that has to do with light. We'll do that in this class. The energy of light is proportional to the frequency. Now, that looks like a V. It's not a V. It's the Greek letter nu. It's a nu. So that really is what is there. This reaction is catalyzed by ultraviolet light. They should have put a UV on there, but they chose not to. They put an H nu. Now, here's what happens. This chlorine molecule, the chlorine molecule is a pretty stable molecule. Those two CLs hang on to each other, and it does take some energy to break them apart. When you shine the right frequency of ultraviolet light onto chlorine, it does cause the chlorine, the two atoms to break apart. So no longer is it a chlorine molecule, now it's 2 chlorine atoms. And I'm going to take a marker, we'll see how it goes here. Oh my goodness. It's a good day. Now each chlorine looks like this. And I know those 2 dots on the bottom are kind of close to it. Stop. I don't want to highlight it. Okay, there. But I want to get rid of that cross thing too. Can't get too close to the board because it does pick up my, my motion. That unpaired electron, in chemistry we call that, it's got a certain name, it's called a radical. When an atom has an unpaired electron, we know the Octet Rule. Octet Rule says atoms are most stable when they have 8 electrons around them. Well, what about when they don't have 8 electrons around them? They go nutty. This thing is a nutty atom right now. It is very anxious about getting an octet again. And I think that's kind of why they call it a radical. It is extremely reactive, so it's going to find something to pair up that unpaired electron. Chlorine especially. The 2 most reactive families on the periodic table. The far left, what are those called? Far left family. Sodium, lithium, potassium, rubidium. Starts with an A. Awesome? Yeah, it's Al something. Oh, yeah, yeah. They're the alkali metals. The alkali. Yep. And over on the almost far right side, noble gases, of course, are not reactive, but right next to noble gases are the halogens. So this is among the most reactive elements. And when it's by itself and not attached to anything, man, it is, and you got 2 of them too. You got this chlorine and then the other one that was in the Cl2 molecule. I think of them as Drake and Josh. They're going to get into something, okay? So what they're mixed up with is this thing. There's just a normal butane molecule, not bothering anybody. Well, when this thing is broken apart, then it's going to attack this molecule. I have the... Didn't mean I just flicked it over there. How about I flick it back here? All right. So, oh, no! I have this chlorine attacking this. Now, it doesn't all just happen in one step. What does happen, and I have kind of a a progression on here. The ultraviolet light first breaks the two CLs apart. One of the CLs attacks this molecule. I have it attacking the second carbon. Does it have to attack the second carbon? No. It could have attacked the first carbon. We're going to find out lower that it actually did prefer that second carbon, and we'll see why in a second. But the chlorine actually rips a hydrogen right off of the carbon. Remember, it's very reactive. It's a rascal, okay? So it's so reactive that it just gets close to that hydrogen and steals it from the carbon off of the butane molecule. Now you have an HCl molecule because that Cl has now grabbed onto one of those H's, and that's where that HCl comes from. The other chlorine comes in and it will bond to the carbon. Now the carbon is kind of left hanging with an unpaired electron. That's very stable or unstable. So the other chlorine is going to go on and attach that. That's where we get that substitution from. The other Cl is going to go onto the carbon that has lost its hydrogen. And that's where that other chlorine winds up. Now I'm going to introduce a couple of terms. I may have even said the terms earlier in the chapter, but I'll try to make it very clear as to what I'm describing. Which of these four carbons is more likely to get attacked by that wild chlorine atom? If there is a tertiary carbon present, that's the one that's most likely to get attacked. This one doesn't have a tertiary, and now you're saying, okay, what does he mean by tertiary? I'll tell you in a second. If there's no tertiary, then a secondary carbon is going to be more likely to get attacked than the primary carbons are. And I'll define those. When a carbon is attached to two other carbons, it's a secondary carbon. A carbon attached to only one other is a primary carbon. There are no tertiary carbons. What do you think a tertiary carbon would be? It's a carbon attached to three other carbons. So, if we have this molecule, my writing is not real good. There's a CH and a CH2 and a CH3. If this CH has a methyl group on it, this carbon right here is a tertiary carbon. 1, 2, 3 carbons attached to it. So if you have this thing that's in a substitution reaction, that carbon right there is probably the most likely one to get attacked. Daniel? More carbons on it, attached to it, yes. Yeah. So that was why, in this example, I had the chlorine attacking one of the middle carbons, not the end carbon. Because the middle carbon is more likely to get beat up. I can't, if you raise your hand and say, why is that? I don't know why. Somebody studied it and decided that in the substitution, those are the more likely product. Do the outside the outside carbons, the primary ones, get ignored? No, some of the chlorines will actually attach to or attack the end carbons, but this is what we would consider the major product, or the favored product. There will be some molecules that will have a Cl that was stuck on the first carbon. It might be like 65% of the molecules would be this, and 35% of the product molecules would be on the end, one chloro. Okay? Yeah.
What would the difference be between the end carbon on the left and then the functional group, the methyl?
This one and this one?
Yeah.
There is no difference. You could say that this is the parent right here. There's no reason. I mean, when we look at it around this carbon,